why we abandoned the fastest rocket engine ever built. During the Apollo era, engineers successfully tested a nuclear rocket engine with nearly twice the fuel efficiency of the best chemical systems, a performance leap capable of slashing a human mission to Mars to just half the time. This proven technology, known as nuclear thermal propulsion, promised to unlock the solar system but was abruptly canceled at the height of its success. Declassified records from Project NERVA and recently revived program studies reveal a story not of technical failure, but of a 50-year pause driven by Cold War treaties, shifting budgets, and terrestrial safety concerns that we are only now attempting to overcome. The fundamental physics of chemical rocketry presents a hard ceiling on our ambitions for rapid interplanetary transit. Every mission launched from Earth is a battle against the tyranny of the rocket equation, a principle that dictates an exponential increase in fuel is required for a linear increase in velocity. This is because chemical engines derive their energy from combustion, a process with a finite energy release per kilogram of propellant. To push deeper into the solar system faster, we need a paradigm shift in propulsion, one that taps into a far more potent energy source. That paradigm was not only envisioned, but successfully built during the height of the space race, in the form of nuclear thermal propulsion, NTP, a technology that works by using a compact nuclear reactor to superheat a lightweight propellant, typically liquid hydrogen, and expel it through a nozzle at tremendous speed. The efficiency of a rocket engine is measured by its specific impulses, a metric analogous to a car's fuel economy, and NTP systems demonstrated an ICE of over 850 seconds in ground. Tests effectively double the 450 seconds offered by the most advanced chemical engines ever flown. According to NASA's own historical analysis, this leap in efficiency would reduce a one-way human transit to Mars from a 9-month slog to a 4-month sprint, dramatically cutting crew exposure to deep space radiation and reducing overall mission mass and complexity. The primary program tasked with realizing this potential was the Nuclear Engine for Rocket Vehicle Application, or NERVA. Operating from the mid-1950s until its cancellation in 1973, NERVA was a joint effort between NASA and the Atomic Energy Commission that systematically solved the immense engineering challenges of building a flight-ready nuclear rocket. Archival test logs from the program document a string of remarkable successes at the Nevada test site, where more than 20 reactors and engines were built and fired. These were not mere laboratory experiments. They were full-scale engine systems, like the Secca Prime, which was successfully started 28 times to prove its reliability and throttling capability. Another test article, the NRX A6 reactor, operated continuously for a full hour at high power, demonstrating the endurance required for a deep space burn. Yet, just as the NERVA program was maturing a flight-qualified design, the political and budgetary ground shifted beneath it. With the Apollo lunar missions concluded, national priorities pivoted away from ambitious interplanetary exploration toward the development of the more utilitarian space shuttle. As documented in congressional records of the period, the immense financial pressures of the Vietnam War and a waning public appetite for large-scale space expenditures led the Nixon administration to terminate the program. The decision was not a referendum on the technology's performance, but a reflection of a changed world, one that no longer saw a mission to Mars as an immediate strategic necessity. The cancellation of NERVA effectively placed a proven, high-performance propulsion system into a deep freeze for nearly 50 years. The NERVA program proved that nuclear thermal engines were a viable, high-performance technology before being canceled for purely budgetary and political reasons. Following the cancellation of the NERVA program, the technical blueprints for a high-performance nuclear engine were not lost, but the world in which they might be built had fundamentally changed. The primary obstacle was no longer one of engineering, but of environment and treaty. During the 1960s, NERVA engines were tested in the Nevada desert, using an open-cycle configuration, meaning the superheated hydrogen propellant, containing trace amounts of radioactive fission products from the reactor core, was vented directly into the atmosphere. This approach, while effective for development, became untenable after the ratification of the 1963 Partial Test Ban Treaty. While aimed at halting atmospheric nuclear weapons tests, the treaty's broad prohibition on releasing radioactive material into the atmosphere effectively outlawed the ground testing methodology that had made NERVA a success. Resuming such a program would necessitate the construction of colossal and costly exhaust containment systems, often called scrubbers, designed to safely capture and filter the entire output of a rocket engine, firing at full power. The sheer scale and expense of building such a facility presented a formidable deterrent to any new development effort. Beyond the challenge of ground testing lay the even greater public and political hurdle of launching a nuclear reactor into orbit. The central question, which persists to this day, is how to guarantee safety in the event of a catastrophic launch failure. Engineering assessments from that period, and continuing into modern analyses, outline a multi-layered safety philosophy centered on ensuring the reactor remains subcritical or cold at all times during atmospheric ascent. Unlike a radioisotope power source, which is always hot, a nuclear thermal rocket is designed to be activated only once it reaches a safe, stable nuclear operational orbit, far from Earth's biosphere. Before activation, the reactor core's radioactivity is minimal, comparable to naturally occurring uranium ore. The critical safety challenge, therefore, is to design a reactor and containment structure so robust that it could survive the explosive forces and extreme temperatures of a launch vehicle failure on the pad or in flight, without its core components reconfiguring into a critical state. This level of over-engineering, while technically feasible and analogous to the proven safety systems developed for RTG power sources on missions like Cassini and Perseverance, added immense mass, complexity, and cost to any proposed vehicle, further eroding political support in an era of fiscal austerity. The confluence of these two factors, the immense cost of treaty-compliant ground testing and the profound political and technical challenge of guaranteeing launch safety, created a powerful and lasting barrier that effectively sidelined nuclear thermal propulsion for generations. The legacy of the Partial Test Ban Treaty and the unresolved complexities of launch safety created a political and logistical impasse that made restarting nuclear rocket development prohibitively difficult for nearly half a century. The half-century dormancy of nuclear thermal propulsion was broken, not by a renewed call for Martian exploration, but by a modern strategic reassessment of cislunar space, vast orbital volume encompassing the Earth and Moon. For this new operational domain, the slow, predictable trajectories dictated by chemical propulsion are a liability. What is required is agility, the capacity for rapid, high-energy maneuvers to reposition assets, inspect unknown objects, or respond to emergent threats. This strategic imperative, as articulated by the Defense Advanced Research Projects Agency, or DARPA, is the driving force behind the demonstration rocket for agile cislunar operations, known as the DRACO program. DRACO represents a fundamental rethinking of how to overcome the obstacles that grounded its predecessors. The first major advancement lies in the fuel itself, where the NERVA program relied on highly enriched uranium HEU, which is considered weapons-grade material and carries immense security and political burdens. DRACO is designed to use high-assay, low-enriched uranium HALEU, DOT, as specified in Department of Energy materials. HALEU fuel is enriched to less than 20%, placing it well below the threshold for weapons material, while still providing the necessary neutron flux to achieve high power density in a compact reactor core. This choice dramatically lowers proliferation risks and simplifies the logistics of handling and launching the reactor, directly addressing a core source of historical political resistance. The second, and perhaps more transformative, innovation is programmatic. Instead of attempting to solve the politically and financially insurmountable challenge of building a treaty-compliant ground test facility, the DRACO program bypasses the issue entirely by targeting an in-space flight demonstration. By launching the reactor cold and inert and only activating it once it has achieved a safe, high orbit, the program avoids the atmospheric testing restrictions of the Partial Test Ban Treaty. This strategic pivot moves the critical validation phase from the politically fraught terrestrial environment to the operational vacuum of space, allowing for a far more direct and cost-effective path to proving the technology. This modern approach, combining advanced materials with a pragmatic testing strategy, reframes the nuclear rocket not as a distant dream for interplanetary science, but as a near-term solution for tactical mobility in a contested domain. By focusing on a flight demonstration using lower enrichment fuel, the DARPA DRACO program is designed to circumvent the treaty limitations and safety concerns that halted NTP development for 50 years. The 50-year pause in developing the fastest rocket engine ever built was never a story of engineering failure, but one of terrestrial politics and treaties. That long-abandoned promise to unlock the solar system is now being revived, not by simply restarting old programs, but by fundamentally changing the rules of engagement. By shifting the proving ground from the Earth's atmosphere to the vacuum of space, modern efforts may finally succeed where their predecessors were grounded. If this analysis of advanced propulsion helps you better understand our future in space, please support Tech Dissect Official by liking this video and subscribing for more. Given the immense potential and the historical roadblocks, do you think the push for an in-space demonstration is the right approach, or are we overlooking unresolved terrestrial safety concerns? Thanks for watching. We'll see you in the next transmission. Next time, we'll investigate the challenge of maintaining a data link across hundreds of millions of miles, and the revolutionary laser communication systems poised to bring interplanetary broadband to reality.